Alright, the last thing we're going to have a look at in this topic is projectile motion with resistance. So in extension 1 we covered the idea of projectile motion in which objects were being projected at an angle against the horizontal, and what we realised is that meant we had to consider movement in both directions, in the x direction and the y direction. In extension 2 we're going to do the same thing, which means we're going to have to consider resistance both in the x direction and resistance in the y direction. Now before we actually look at projectiles being moved against the horizontal, we're just going to have a look at particles that rise and then fall. So if an object starts from Earth and then travels up to a maximum height and returns to Earth, to simplify our calculations, we're going to use the Earth as the origin for the upward flight, with upward motion being positive, and then we're going to do kind of a second question, moving downward motion as the origin, the turning point, is the origin, and downward flight is positive. So exam questions on particles that rise and then fall tend to have many parts which cut people off, but the individual parts are simple because you can make a proper start on each of them, but the best thing to do is to split it up really into two questions, a rising question and then a falling question. Alright, something very important. When we're launching straight up or both, I've talked about this before, we're dealing with x dot despite it being in the y direction. This is the only case, this is, as I said before, is only the case if the movement is in one dimension. Okay, we're going to start with this example. It's very, very wordy and it's quite tricky, but we're going to have a go. Okay, so a capsule has mass m, is fired straight up with u meters per second. On the upward flight, air resistance is negligible and the magnitude of acceleration due to gravity is g. The capsule then deploys a parachute and falls back to Earth, subject to gravity and a resistance of magnitude kv squared. Part 1, we're going to use calculus to show the maximum height obtained by the capsule is h is u squared on 2g. Okay, this is going to just use our work with extension 1. We know that as I'm moving up, x double dot is equal to minus g. Again, we're dealing with x double dot because this is one-dimensional travel. We're only going up and then down. We're not going back and forwards. If we integrate that, we can't actually. We want u squared is h on 2g, which is implying when we think of maximum height, we're thinking my velocity is 0. So we want something that involves x and velocity. Okay, so we're going to go v to v dx. That's going to get us x and velocity. V to v dx is equal to minus g, which means that dv to x is equal to minus g on v. I'm sure there's many ways that you could do this question. You could probably use something that involves time and then find the maximum time to get to the height. But it's going to be easier just to go, okay, maximum height is when velocity is 0, so I want an equation involving x and velocity. Okay, right, now we want to integrate this, but we need to integrate with respect to v because my equation is in terms of v, so we're going to have to flip it upside down. Dx to v is equal to minus v on g. Now we're starting with an initial speed of u. So when we're going to integrate this, we're going to integrate from our initial x is 0 to some unknown x, and here we're going to integrate from our initial velocity u, and we want to know maximum height, so that's going to be when my velocity becomes 0. We've got a minus 1 on g here, and we've got a v to v here. Okay, integrate that, we get x between 0 and x, which is just x, and here we get minus 1 on g of v squared on 2 from u to 0. So that's going to be minus 1 on g of 0 minus u squared on 2, which is positive u squared on 2g is equal to x, which I think is what we wanted to prove. Nice. So therefore, height max is equal to u squared on 2g. All right. Part 2 says, for the return trick, take the origin to be the point as it begins falling. Point as it begins falling. Let's highlight that. The origin. And assume down is positive. Show that the motion is determined by that equation there. Okay, so we're going to start with mx double dot is equal to, now if I'm moving down, the force of gravity is positive. And we've also got a resistive force, multiplying it by m, kv squared. Again, you don't have to multiply it by m. In the HSC, they're going to be very specific of what to do and what not to do. And in this instance, we're going to multiply by m because there's no m's in the equation. We're multiplying this by m, if that wasn't clear. Cancel both the m's, we're going to get g minus kv squared. Now notice that there's a k outside of here. So if we take out a factor of k from g, we're going to have to put it g on k. Now we're told in the question that alpha squared is g on k, so we can replace this with alpha squared. Done. Okay, part 3 says let u be the impact speed of the package. Prove that u squared is alpha squared 1 minus e to the minus 2kh. Okay, we do know that x double dot is equal to k alpha squared minus v squared. And we want something involving velocity because that's a speed. And involving h, so really something involving x because h is a height. Right, so we want x's and we want velocity, so that's v to v dx. Right, we're going to have to divide everything by v, which is not going to be pretty. So v to v dx is going to equal, we might take the 1 on k out the front, times by alpha squared minus v squared on v. And we have to integrate with respect to velocity because it's in terms of velocity here, so we're going to have to flip it upside down. dx onto v is equal to, I don't know why 1 on k appeared there, that's just a k there. I haven't flipped anything upside down yet, I think I was ahead of myself. That k is there, and I've just divided the v down to there. Now we put 1 on k if we flip it upside down. Alpha squared is going to be on the bottom, so it's going to be v over alpha squared minus v squared. Now in an ideal world we want a 2 on the top, which means I'm going to have to put a 2 down here. We want to integrate that, so it's going to be minus 1 on 2. We might have a look at our bounds in a second. Minus 1 on 2k ln of alpha squared minus v squared. Now we might use our bounds for this one. We're just going to consider what we're integrating with respect to. Here we're integrating from 0 to x. We're starting at 0 and we're going down to some point x. And here we're starting at, let's see where we're starting. We're starting at, what's our speed? We're firing straight up. Now u is the impact speed. Now when I'm at the top of my motion, well, the very top, it stops and then it starts going down. So it's initial velocity because when you get to the maximum height, your initial velocity is 0. So we're integrating to 0 down to our impact speed of u. So we're integrating from 0 to u. Okay, so this is going to be x. Now in this instance, let's just think about what we're doing in this question. We're told that we want to know, we're told that we're trying to prove the impact speed. So the impact speed is another way of saying, hey, when is my equation, when is it hitting the ground? That's my impact speed. Now, I'm falling, it's falling down and hitting an impact speed, and the distance that it's fallen is just whatever its maximum height was. So its maximum height was h, and if I'm starting and going down, well, I've fallen h meters. So this is h equals minus 1 on 2k. Let's evaluate this integral. ln of alpha squared minus u squared minus, we put in a 0, it's going to be ln of alpha squared, which might be useful later to note that's 2 ln of alpha, but we'll see. Let's go down here. So we're going to multiply this up to here. So minus 2kh equals ln of alpha squared minus u squared minus ln of alpha squared. Now we can combine those ln's using our log laws. So minus 2kh equals ln of alpha squared minus u squared on alpha squared. It wouldn't have been useful to do what I mentioned before and put that 2 down to there, because then we couldn't combine it with this ln here. Now we might raise everything to the e, so alpha squared minus u squared on alpha squared is equal to e to the minus 2kh. I don't know why that h became lowercase, we'll make it uppercase, which is looking pretty good because there was a minus 2kh in what we're trying to prove. So let's have a go at making u squared the subject. So alpha squared minus u squared is equal to alpha squared e to the minus 2kh, which means moving everything over, u squared is going to equal alpha squared minus alpha squared e to the minus 2kh, which means u squared is equal to alpha squared 1 minus e to the minus 2kh. Nice, done. That's what we're trying to prove. Alright, part 4. Assume that the package is launched at a speed of u is equal to alpha. U is another way of saying initial speed. We use that a lot in physics. U, we say, is initial speed. Lowercase u, not uppercase. Find the impact speed as a percentage of the launch speed. Okay. So we want the impact speed, which is capital U, over the launch speed, which we've defined as lowercase u. And we want to know that as a percentage, so times by 100. Right, now we know the equation for whatchamacallit, u is this here. So we do need to square root that. So we want to know the square root of alpha squared 1 minus e to the minus 2kh over, we're told that the launch speed u is alpha, and we're timesing that by 100. Alright, we're going to have to do some simplifying here. Now, there's an alpha squared here, which means we can take that out the front of the square root. So alpha square root of, we've got 1 minus e to the minus 2. Now, we're told we're told in the question initially that k is, we don't know what k is, but we do know that alpha squared is g on k. And we also know that h is u squared on 2g. I might write that down over here. H is u squared on 2g. And what else do we know? H is u squared on 2g. We also know that alpha squared, what did we say alpha squared was? G on k. So we've got minus 2kh. So I'm thinking we might have to do a little bit of rearranging here. So we know that h is u squared on 2g. And what is u squared? U squared is the initial launch speed. And we're told in the question that the launch speed, the initial launch speed, is alpha. So u is equal to alpha. So this is telling me h is alpha squared on 2g. So let's substitute that in. Minus 2 times by k from this equation is going to be g on alpha squared times by h, which is alpha squared on 2g. So I think everything there is going to cancel. That's going to cancel with that. That's going to cancel with that. That's going to cancel with that. And we're still over alpha times by 100%. I'll add that in a second. That will cancel with that. And we've got 100, that's our percentage, times by the square root of 1 minus, everything here is cancelled apart from the negative, so it's e to the minus 1. Right, and if we type that into our calculator, it didn't look like everything was going to cancel, but it ended up being pretty nice. All right, if we do that, we get 79.5%. That's quite a very challenging question. I reckon the most challenging bit, honestly, was this substitution at the end. Realizing again that U was alpha and all of that. Okay, projectile motion now with air resistance. So when an object experiences air resistance at an angle to the horizontal, we can say a few things. Number one, it has a lower maximum height. Makes sense. Lower maximum height because there's a resistance. Number two, it has a shorter range. Number two, shorter time of flight. Number three, it descends more steeply than it's climbed. Normally, projectile motions exist in a parabola, but when there's resistance, it's going to go a bit like this. And it's also not going to be a parabola, which is going to be very important later. There's going to be often something involving exponentials and differential equations. It has a lower velocity, and also, if I've got resistance, that means my x velocity is no longer constant. In extension 1, we've assumed that x velocity is constant, which is false. Now, if there's a resistive force acting against your x velocity, and it's not a rocket, which means there's no force propelling it along, that actually means your x velocity is going to approach 0, which means your velocity is going to approach your y velocity. Right. Because of that, your y acceleration, is going to be approaching 0, which actually means your y velocity is going to approach its terminal velocity. So this is different to extension 1, where y double dot is a constant gravity. Due to resistance, y double dot will approach 0. In other words, the particle will approach its terminal velocity. So as my particle's moving down, yes, gravity is moving down, but air resistance is also resisting that motion. So eventually your y velocity is going to approach its terminal velocity because your acceleration due to gravity is being opposed by air resistance. So eventually they'll cancel each other out and there will be 0 net acceleration. Although we have talked about the fact that an object can never reach its terminal velocity, it will just approach it like an asymptote. Okay. Multiple choice. We've got a particle is projected with a velocity of 40 meters per second at an angle of 30 degrees to the horizontal in a resistive medium. It reached a maximum height of 15.5 meters and lands 87.4 meters away from its projection point. Which of the following statements cannot be true? Okay. The maximum height occurs when the particle has moved 48 meters horizontally. Well, we know a particle in resistance has a shorter maximum displacement, and the maximum displacement has to be shorter than 87.4. And we also know that maximum height occurs at half of the maximum displacements. The maximum height would have to occur at less than 47.3 meters. So this one is impossible. The velocity at impact is 24 meters per second. Well, let's think. So we've got the velocity at impact is 24 meters per second. Well, the velocity of impact has to be less than... No, it has to be... What did we say? Let's think. It lands at a lower velocity. What else do we know? It descends more steeply than it climbed. So no, the angle of impact would have to be bigger than 30 degrees because it's descending more steeply. We also know that it's going to have a shorter velocity. I think I've written that down here. It lands at a lower velocity. So no, it can't be that. Well, I guess it could be that one actually. Velocity at impact is 24 meters per second. That does make sense. The angle to the horizontal is 24 degrees. No, it can't be that one because it is descending more steeply. So its velocity has to be, the angle has to be bigger than 24. So it has to be B. Okay. All right. Something that's going to be quite important is splitting air resistance into horizontal and vertical components. So air resistance acts in the opposite direction to the motion of the particle. So as the particle changes direction and the magnitude along its trajectory, the direction and magnitude of the air resistance changes as well. So to create equations of motions, we need to split the air resistance, into horizontal and vertical components. The most basic form of air resistance in projectile motion is linear drag. So linear drag is when resistance is proportional to its velocity, not proportional to its square of its velocity. And this is the most common one. Okay. A particle moving with velocity v in a medium with resistance to motion is proportional to its velocity in the opposite direction. We have to prove that the vertical and horizontal components of the velocity are minus kx dot and minus ky dot. Okay. So to do this, we're going to use our triangle, and we're going to say the resistance in the x direction has to be the resistance in the y direction, r, multiplied by cos theta. Theta. Now we also know that x dot, well, if the velocity is v, if we have a triangle with v velocity, alpha and velocity, x dot is going to equal v cos alpha. Right, so we've decided that the resistance is r cos theta, cos alpha I should say, cos alpha. But the resistance is minus kV, so this is minus kV cos alpha, but v cos alpha is x dot, so this is minus kx dot. Okay, and we have a look at the y direction, so we know that y dot is equal to v sine alpha, but if we resolve in this direction, we also know that ry is equal to r sine alpha, so this is r sine alpha in the y direction. So here we've got r sine alpha, and here we've got r cos alpha, and over here we've got v sine alpha and v cos alpha. But r we've already said was minus kv, so minus kv sine alpha, but v sine alpha is y dot, so this is minus ky dot. Done, we've proven those two things. Alright. Quadratic drag is something that is up for contention in the syllabus because technically you don't have to know how to do projectile motion with quadratic drag, but they have asked multiple choice questions, so it's something important that we are going to learn. So here we've got a particle moving in a resistance where the motion instead is proportional to the square of its velocity. And we have to prove that the resistance in the x direction is that and the resistance in the y direction is that. Okay, so a couple of things. We know that we've got alpha here, this is velocity, then this is going to be v cos alpha, that's x dot, and this is going to be v sine alpha, that's y dot. And if we resolve this here, rx is going to equal r cos alpha, but r in this instance is minus kv squared cos alpha, which is minus kv times v cos alpha. So v cos alpha is x dot, so we do have left over a v, so we've got minus kv x dot. Similarly in the y direction this is going to be r sine alpha, but r we've decided in quadratic drag is minus kv squared, again it says proportional to the square of its velocity, which is minus k, oh sorry, I missed a sine alpha there, minus kv times v sine alpha, but v sine alpha we've decided is y dot, so this is minus kv y dot. Okay, a bit of controversy with this idea of quadratic drag. Some textbooks give an incorrect understanding of quadratic drag, and they give incorrect formulas. And the kind of contention around these are the correct formulas here, and the textbook I'm using uses the correct formulas. The textbooks that use the wrong formulas don't quite understand quadratic drag very well. And the reason we're not focusing it on a lot is because it's not in the syllabus. You don't have to know how to do quadratic drag in actual projectile motion questions, only in basic multiple choice questions. So we're not going to focus on it. The only example we're going to do on it is as far as they will go, and this is just quite a basic question we're going to do. Something though that we're going to make very obvious in a second is that these equations here are not what we've seen before for resistance. Normally we've seen like kV or kV squared, and it's been really easy to integrate and differentiate those. But these are not the same because I've got x dots in here, and we're going to realize eventually we're going to have equations like x double dot acceleration is minus kx dot. And it's not so straightforward to work with this because this is an equation in this form. We're going to have to work with these differential equations, and the reason we can't work with quadratic drag is because these equations exist in the form minus ky y dash equals y double dash, which is an equation unfortunately that we can't solve. So quadratic drag, we can't use normal calculus to solve them, which is why we can't do it in extension 2. Okay. Vertical and horizontal acceleration in linear drag, and then we're going to quickly look at quadratic drag. So for linear drag, and I've written a couple of hints and tricks down here, something that I found useful when I was doing these questions. So we've decided that drag in the x direction is minus kx dot. So since drag is a force, we're going to say that mx double dot is minus kx, because that's our drag and that's our force F equals ma. Now if we want to divide both sides by m to get an acceleration equation, we would get this equation here. And in the y direction, now projectiles will have equations. Now because my object is moving down in projectile motion, we've got minus mg minus ky, so the negative gravity force, and then we're taking away the drag again. And if we want to divide by m, the m's here, that will cancel, and we're going to divide by m. Now, so a couple of important notes. Sometimes the equations for x double dot and y double dot are given and not required to be proved. So they could be given as x double dot is minus kx and y double dot is minus g minus ky dot. But you notice in these equations up here we're dividing by m. Importantly, if these equations are given to you, you do not need to and do not prove them this way by starting here and dividing by m. That is because these k's here, that k there and that k there, already have factored in a division by m because there's no m here. So these constant k's have already factored in a division by m, so we don't need to divide by m again. If you try to prove them and come up with your own value of k, you will get the answer wrong because the value of k in their assumed equations will be different to the value of k that you have found. So don't do that. And also when we're working in 2 dimensions, we're not going to ever use that multiplying by m trick. Okay, quadratic drag, the same idea. Again, we're not going to focus much on quadratic drag, but here you notice the only difference is there's velocities here. Okay. This is as difficult as quadratic drag is going to get. Okay, a particle of mass 10 kilos is moving through a medium where resistance is proportional to the square of velocity. At a point in its flight, we've got x dot is 12 and y dot is 5. If its terminal velocity is 100 and g is 10, find the horizontal and vertical acceleration of the particle. Alright, we're going to start with our definition of quadratic drag. mx double dot is equal to, let's go up, minus kvx dot. Okay, and in the y direction, we've got y double dot is equal to minus mg minus kvy dot. And we've got an m there, sorry. My double dot. And those are our two definitions of quadratic drag. Now, we've got a few things that we know. We know first of all that this coordinate exists, but terminal velocity is something that we know as well. So terminal velocity is 100 and gravity is 10. The reason we're going to start using our terminal velocity is because terminal velocity occurs when your y acceleration is 0. So we're going to do that. Mass, which we're told is 10, times by 0, is equal to minus 10 times 10, which is gravity, minus k times by, we're told the terminal velocity is 100, and we know y dot, well, your y velocity when you're at your terminal velocity is 100. That's something we learnt before. When you're at your terminal velocity, your x velocity is 0. That's because as a particle is moving along, its x velocity is approaching 0 due to air resistance. So if you're at your terminal velocity, that means your x velocity is 0. So that's my velocity. What have we got? That's my velocity there, and my terminal velocity is 100. So my velocity is here, and my terminal velocity is that velocity there. Okay. If we have a go about it solving that, we're going to get k is equal to minus 10 times 10 divided by 100 times 100. So minus 10, so minus 100 over minus 100 times 100, which is 0.01. 100 times 100. Oh, yeah, that's right. Is equal to, I feel like I've done something wrong here. K is equal to, yeah, 0.01. Yeah. K is equal to 0.01. All right. The next thing we're going to do is we're going to substitute that into some equations. Now, I think, so we've got the y acceleration is 0, so minus 100 times 100. Yeah, I can't see any mistakes here, so k is equal to 0.01. So now we've got mx double dot is equal to minus kv x dot. And we want to know the horizontal and vertical accelerations. Okay, right, so mx double dot, now m is 10, so 10 times by x double dot is minus k minus 0.01 times by, the velocity at this particular point is, let's have a think, at this particular point in time, the velocity we know is, we're told at this point it's 12, and the y is 5, so that's going to give us 13. So that's our velocity at this particular point in time. This velocity here is kind of like the total velocity, not the velocity in either the x or the y direction. It's kind of like the magnitude of your velocity. And then x dot, we've decided, is already 12, so times by 12. And we're trying to find x double dot. So if you have a go at finding x double dot, we've got 0.01 times 13 times 12 divided by 10. We get 0.156. So x double dot, and there's a minus there, so minus 0.156. And then we just need to use the fact that my double dot is equal to minus mg minus kvy dot. So 10 times y double dot is equal to, the mass is 10, gravity is 10, k is 0.01, the velocity we've decided is 13, and at this particular point in time, y dot is 5. If we just have a go at solving that equation, we're going to get minus 10 times 10 minus 0.01 times 13 times 5, close bracket, divide 10, we get minus 10.065. Right, so that's our y dot, y double dot, and that's x double dot. that is probably even more tricky than what they're allowed to ask you in quadratic drag. Quadratic drag, again, technically not really in the syllabus, definitely not in what we're about to do, despite what some textbooks do with these harder questions. Okay, now we're actually going to apply projectile motion and resistance into a question. Now they can't ask you 3D projectile motion questions with resistance. I don't even think they can ask you 3D projectile motion without resistance. So some textbooks do, but they don't. You can't. It's not in the syllabus. Okay, example 7. We've got a particle of mass n is thrown from the top of a very tall building with an initial velocity u at an angle of alpha to the horizontal. The particle experiences an effect of gravity and a resistance proportional to its velocity both in the horizontal and vertical directions. The equation of motions in the horizontal and vertical directions are given by this. Right. Importantly, you are not required to show this. If you do try and show it, this value of k will be wrong because this value of k already has a division by m factored into it. So your k's here will be wrong and your k here will be wrong. Okay, we need to, first of all, in part 1, derive the result x dot is minus ue to the minus kt. Okay, initially our equation, we're told the equation in the x direction, so part 1, x double dot is equal to minus k x dot. Okay, and we need to have a go about solving this. Now we want to solve, we want x dot to be the subject and k it to be in terms of time. So we want to use the fact that acceleration is to v to t, so minus kx dot. And we want to integrate with respect to time. Quite tricky though, because we've got x dots here. Now this is actually a differential equation in the form y double dash is equal to minus k y dash. And we need to try and integrate this. You could as well, if you wanted to, if you treat x dot as a letter, we could say this is dx to t is minus kx. And if we do that, well, you're going to have to divide both sides by x dot, because remember velocity is another way of saying x dot. So we could say this is dx dot to t. Divide both sides by x dot. We could say this is 1 on x dot, x dx dot is equal to minus k to t. Now, the integral of this is ln of x dot. So ln x dot is equal to minus kt plus c. Okay. Right, now we have to think the particle is, what do we think? Initially with a velocity of u. So its initial velocity is u. Okay, let's think about that. Initial velocity is u, where alpha is our angle. So x dot, the initial x dot is u cos alpha. The initial y dot is u sine alpha. So when t is 0, this is going to be x dot. Or x dot is u cos alpha. Okay. So that means that ln, the initial velocity, is u cos alpha. Now that's when time is 0, so this is going to equal c. So c is going to equal minus ln of u cos alpha. So therefore my equation is ln x dot is equal to minus kt minus ln of u cos alpha. Okay. So there's a couple of things that we could do here. I'm just checking so far that we've got everything right. I'm feeling like there should be a positive somewhere. No, it's looking like everything so far is right. Equal minus kt minus ln of u cos alpha. No, that's looking right. So c is minus ln of u cos alpha. I'm just quickly checking that I haven't made any mistakes. Ln of x to u cos alpha minus kt plus c. Ln of u cos alpha 0, so c. Oh, no, okay, so I have made a mistake. So if that's 0, then C is just going to be positive ln of u cos alpha, not negative. There we go. So that's a plus there. Right, and we want to make x dot the subject. So x dot, we raise everything to the power of e, so minus kt plus ln of u cos alpha. Now that's just e to the minus kt times by e to the ln u cos alpha. And e to the ln of something is just what's inside the bracket. So this is e to the minus kt ln, sorry, not ln, u cos alpha, which I'm pretty sure is what we were going to prove. Let's just check. Nice, done that. Beautiful. Okay, we've got to verify that y dot satisfies that equation. Okay, let's have a think. So we're told in the question, well, we know that y double dot, let's think what y double dot is equal to. Y double dot is equal to minus ky dot minus g. Okay, now the trick with this question is that this is not a separable differential equation. So we can't do the same thing as what we did before. What we might have to do is work with what we're trying to prove and prove that it satisfies this. So the question tells us that y dot is equal to 1 on k outside of ku sine alpha plus g e to the minus kt minus g. Okay, and now this is in terms of t, everything else is a constant, so we can just differentiate this and get y double dot. If we differentiate that, what are we going to get? The only thing, these are all constants here, so we can just differentiate that and get minus k, and that's going to cancel with this 1 on k, so that's minus and of course this g will differentiate to get 0, so minus ku sine alpha plus g e to the minus kt. Right. So that's our differentiation there. That's y double dot. And we have to prove that it's in this form here. So I guess what we need to is we need to somehow get this into the equation. So if we pull out a factor of k from the front, or minus k, pull out a factor of minus k from the front, we're going to have 1 on k, ku sine alpha plus g, e to the minus kt minus g, and then we need a minus 1 more g. Yeah, and if we expand that, you're going to get the same thing. So this is going to be minus ky dot minus g. Right. So we've proven it satisfies the differential equation. That is what we were trying to prove. But at the initial condition, we do need to prove that the initial condition, so when t is equal to 0, we need to prove that y dot is equal to u sine alpha. So we're going to probably work with this one here. Or where do we want to work? Yep, that one there. So y dot is going to be 1 on k, ku sine alpha plus g minus g, which is, the g's will cancel 1 on k, and that's just going to be ku sine alpha, which is u sine alpha. Done. All right. Still a couple parts to do. Okay, part 3. We're told that what is the value of t when the particle reaches its maximum height? Well, the maximum height of a particle occurs when y dot is 0. And we've decided that our equation for y dot was 1 on k, ku sine alpha, plus g e to the minus kt minus g equals 0. So if we have a go about solving that, the 1 on k's will die, and we're going to get ku sine alpha plus g multiplied by e to the minus kt equals g. Now these are just constants, so we can divide them over. So e to the minus kt is equal to g over ku sine alpha plus g. And then if we have a go about solving that, that's just going to mean t is minus 1 on k ln of g on ku sine alpha plus g. Okay, part 4 says, what is the limiting value of the horizontal displacement? Right, we do know that we've already decided that our horizontal displacement, well, we know that x dot in this question, we've proven that x dot was u e to the minus k2, u e to the minus kt cos alpha. And we know the limiting value, which means the maximum it can get. Now we know the integral of x dot is displacement. The integral of velocity is displacement. So we're integrating from our starting displacement of 0 to the limiting value, which is just the maximum it can get. In other words, what is the displacement at time is infinity. Now u cos alpha is a constant, so e to the minus kt. So if we integrate that, we're going to get minus u cos alpha on k, and then we've got e to the minus kt. That's because the integral of that is minus 1 on k e to the k from 0 to infinity. Okay, so this is going to be minus u cos alpha on k. Now e to the infinity, well, e to the minus something on infinity, this graph looks like this. So minus e is approaching 0, so e to the minus infinity is going to be 0. So 0 minus, this will become e to the 0, which is 1. Okay, so the limiting sum, if we expand that, that's going to become positive u cos alpha on k. So that's the limiting sum. Okay, last example for the video, we're just going to do example number 1. And this is going to be a trick with dividing the mass that we have been looking over in previous examples. So a particle of mass m is projected from the origin with an initial velocity of v at an angle of theta to the horizontal. The particle experiences gravity and air resistance proportional to its velocity. Right, so we're going to start with our definition of a linear drag in the x direction, which is, let's think, linear drag in the x direction is minus kx dot. Okay. But in this instance, we notice that there's an m in the equation. So we're going to start with our definition because the equation hasn't been defined for us. So we need to start with mx double dot. If it's not defined for you, if you're not just given this in the question, then you need to put an m here. Then we're going to say mx, or x double dot, is equal to minus k on mx dot. Now we can say, okay, well, x double dot is to v to t, but velocity is another way of saying x dot. So this is to x dot to t is equal to minus k on m. And then we can say, or x dot, we can say 1 on x dot dx dot is equal to minus k on m dt. And if we integrate this, we're going to get ln of x dot is equal to minus k on m t plus c. Now we know that its initial velocity is v, which means initial velocity in the x direction, x dot, is going to be v cos, let's see, is it theta or alpha? Theta. Equals, that's going to be 0, so equals c. So therefore ln of x dot is equal to minus k on mt plus ln of v cos theta. We raise everything to the power of e, we're going to get x dot is equal to e to the minus k on mt v cos theta, which I think is what we wanted to prove. Yep, nice. Yeah, done. All right, thank you. Well done, we've finished mechanics.